Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing the risk assessment and the reliability of the spacecraft system. So, in the last session we discussed that is the mean time failure for a satellite, considering it is having a maximum lifetime u, means after this time the satellite will not work. So, then we modified this that is the that exponential that is the probability density function, that is lambda e to the power minus lambda t. So, this one we modified and we are able to write this as for this equation for this probability density function f t that we wrote. So, this is lambda e to the power lambda t when less than u, and then we write it to be lambda u, then lambda e to not lambda, this lambda term was not there. So, it was delta, that is the Dirac delta function u when t is greater than or equal to u. So, this is the function we took, and then we found we could determine the mean satellite lifetime, this is given by tau by this expression. And then we solved an example also to show that is how this probability it depends on this ratio, that is what is the maximum lifetime and what is the mean time to failure. So, I said already that is tau by t, it is the probability that the satellite can fail in a random manner. So, this is and we have seen how to calculate this probability. Then we just we started discussing that is the satellite system availability. So, we will continue with this in this session. So, we will consider two configurations for this satellite system availability. So, one is without backups, there is no backup satellites. So, along with the active satellites, but there are the backup satellites along with the active satellites. Then if our next topic will be to discuss the system reliability. So, I was talking about the satellite system availability. System availability. So, this depends, means whenever it is needed to provide a service, it can be navigation, communication, or it can be remote sensing. So, what you need that what is the required time. So, the first we will consider the required time, we will consider. So, required time is the, so because we defined the satellite ability is the that is the required time minus the downtime divided by the required time, that we defined it in our last session. So, I write that is the required time is L, then what is the number of satellites, the next is the number of satellites that are needed, number of satellites that are needed or needed to be launched during this required time, during this time L. Okay. So, this I will define as N. Then we will put one A, this is the availability of the system. Then for each satellite there is a time which is required for the that is to replace a satellite. Suppose a satellite has failed. So, the time required to replace a satellite. So, this is the time required to replace a satellite. Here, then whenever we launch a satellite, so there is the probability whether the launch will be successful or it will be fail. So, again there is a probability. So, we will define P as the probability of successful launch. Okay. So, as I already said, we will consider, in order to derive this availability A, two cases. So, the first case we will consider there is no backup satellite in the orbit, and second is there is the backup. Now, suppose tau is the mean satellite failure time, is the mean satellite failure time then you can write S is equal to L by tau. So, the number of satellites. So, this gives the number of satellites to be replaced. Okay. So, if I know what is the satellite, the mean satellite the time or the lifetime. So, it is not failure time, I should write it is the mean satellite lifetime. So, if I know the mean satellite lifetime tau, so then I can know what is the number of satellites to be replaced in the required time, that is required service period L. Now, since P is the probability of successful launch of a satellite. So, the number of satellites which need to be launched, you can find it from the number of satellites to be replaced divided by the what is the probability of the successful launch. So, the number of satellites, to be launched, the number of satellite to be launched I can write n is equal to S by P. So, then I can put this S here and then I can write L by it is P into tau. Now, what is that? We know already what is the expression for the tau. Tau is the mean time failure of a satellite. So, this I can write P into the mean time to failure minus 1 to the power e to the power minus u by t. Okay. So, if I want to know what is the number of launches per year, so the launch per year I can write n by L is equal to 1 by P t 1 minus e to the power minus u by t. So, we have written n is equal to L divided by p t into 1 minus e to the power minus u by t. Okay. And what is S? S is, that is the number of satellites to be launched, it is the L by tau. So, this is the number of satellites, and when you consider then now the during the maximum lifetime, during the maximum lifetime u, the probability that a satellite fails is given by, that is P of A is equal to 1 minus e to the power minus u by t. So, this is actually tau by t. So, I can write, therefore, I can write S is equal to L by tau, this one, and then this will be L divided by P A into t, which means that P A into S is equal to L by t. So, this will actually we will use, we are writing this because finally we will put this in order to write the availability function in terms of L. So, that is why I am writing this. So, it is probability of the failure multiplied by the number of satellites will be equal to L by t. So, in L years there are S replacements to be performed Okay. Now, if each satellite needs TR time for replacement if it succeeds the launch, if it succeeds in launching, so time for replacement. So, the time for replacement we can write time for replacement will be, it will be T R by P, because this it depends on what is the probability of a successful launch. So, if it fails, or suppose if there is the probability that it will certain that there will not any failure, in that case it is the same, but there is always a probability of a failure or failure. So, that is why the time for replacement is given by T R by P. So, now we can write the time duration of unavailability time duration for unavailability during L years, So, this I can write by P S P A, that is the P A, this is the mean time of the satellite failure multiplied by the number of launches, then this is the the time to replace one satellite. So, it is T R by P. So, this already we wrote, that is that is P A into S is equal to L by T. So, this I can write. So, this I can write is equal to L T R by P T. So, the mean, so therefore, the mean unavailability that is the breakdown rate is so I can write B. So, I can just divide it by, so it is small t actually, not capital T here. So, I can divide this by L and I can get B is equal to T R by P into T. So, I can find the availability A is 1 minus B, and this is given by 1 minus T R by P into T. So, this is a very important relation to be remembered. Okay. Now, we will consider the case for the backup satellite. Backup satellites. So, here what we will assume? We will assume that each satellite has a backup satellite. Each satellite has a backup satellite, and we will assume that the backup satellite, also will assume that the backup satellite has constant failure rate gamma and maximum life u, which are identical to that of the active satellite, So, since each satellite is having a backup satellite, so in this case the launches required per year will be just the double. So, I can write straight away that is the n is equal to what we have derived in the earlier case, the no backup case. So, as compared to the backup case, it will be that 2 times. So, it will be 2 L divided by P T 1 minus exponential u by T. Okay. So, considering the fact considering the fact that both the active and the redundant satellites have independent performances means we are considering they are independent, means this in the probability theory we use the independent events. So, both the event we consider, this is the independent, and the same parameters, in the same parameter, that is the P is equal to launch success and TR is time to replace a satellite. And all other parameters like like T, then U, that already we said. Then we can show that this availability is given by 1 minus 2 T r square divided by P t square. We will take one example. So, example. So, let T r is equal to time to replace a satellite is equal to 0.25 years. This is T r. Then the probability of successful launch P is equal to 0.9 and the mean time to failure MTTF is equal to 10 years. And maximum life U is equal to 5 years. So, we are to asked to find the that is the availability, find the availability, find the satellite service availability for both the cases. Okay. So, first we have to find that is the mean time, satellite mean time to failure. So, tau will be given by T 1 minus e to the power minus u by T. So, this already we have found out in the previous example. So, this will give 3.99 years. So, u is equal to 5 and T is 10. So, you get this figures. So, and the probability of failure, that is P A is equal to 0.39. Okay. So, the number of launches per year when no backup is placed. Okay. In the previous question, you have to put also the number of satellites per year in both cases, number of satellites launching per year for both the cases. Okay. So, we will find this n by L already we know of, that is for no backup. The formula is given by 1 by P into tau, and you can calculate this to be equal to 0.28. So, I can approximate into 0.3. What does it mean that? Which means 3 launches per 10 years. Okay. So, next you can calculate the availability. So, availability formula A is equal to 1 minus T r by P t, where T r is the time for replacement. So, I can write this is equal to 1 minus 0.25 divided by 0.9 into 10. So, this will give me a figure of 0.9722. Okay. So, what does it mean? The availability is the availability in this case is 97.22%. Now, for the other cases, in the backup case, so backup case, so your number of satellite launches, so this is n by L, it will be just the twice. So, you will get it is 0.56, which I can write to be it is 6. So, here in 10 years, the total satellite launches is equal to 6. Okay. Now, you can calculate the satellite availability A is equal to 1 minus 2 T r square divided by P square T square, and if you substitute these values 1 minus 2 into 0.25 whole square divided by 0.9 square into 10 square, you can show this is will be equal to 0.9985. So, what does it mean that it is the satellite is available, the satellite service is available, satellite service is available 99.85% if you have the backup. So, we will discuss more on this in our next session. So, I end it here. Thank you very much.